During the height of the Cold War hysteria of the 1950s, SAC, or the Strategic Air Command, America's nuclear strike force, was looking at the next generation of nuclear delivery systems. Bombers were the backbone of SAC, but were slow and vulnerable to Soviet air defences. ICBMs were still in their early stages and not yet reliable enough. But from research into nuclear-powered jet engines came an idea for one of the most insidious weapon systems ever devised.
Furious Droid.
As the Cold War developed and deepened, both the US and the Soviets scrambled to create ever more effective ways to deliver and defend themselves from nuclear attack. In the US, a system was proposed that the nuclear planners would call the Big Stick. In a little over 10 years since the first atomic bombs had been dropped on Japan, the technology had moved on rapidly. SAC had a fleet of long-range nuclear bombers using the B-52, keeping a number of these in the air 24 hours a day, 365 days a year, flying around the Arctic on constant alert. One of the problems with the jet bombers of the time was that they were limited by their fuel capacity to fly around whilst on alert. To combat this, the US set out to develop a nuclear-powered bomber. If this could be done, then their flight time and range would only be limited by how long they could keep the crew up there. However, they soon found out that the shielding required to protect the crew from the nuclear-powered engines weighed so much that it made them slow and used up most of the payload capacity. Not to mention the handling problems of such a dangerous propulsion system for the ground crew. But from this research came a ceramic reactor core, small enough to be used in an unmanned plane or cruise missile that wouldn't need any heavy shielding. In 1955, the US Atomic Energy Commission asked the Lawrence Radiation Laboratory to do a feasibility study on using the new ceramic reactor to power a ramjet engine. And in 1956, the USAF issued System Requirement 149 for a nuclear-powered winged missile. The project was called Pluto after the code for the ceramic reactor developed by the Lawrence Radiation Laboratory, and the name given to the cruise missile was SLAM, or Supersonic Low Altitude Missile, but also it was unofficially known as the Big Stick. Although ramjets were quite well known at the time, no one had proposed using a nuclear reactor as the heat source instead of the usual solid rocket fuel or liquid fuel. A ramjet works by using the forward speed of the vehicle to compress the air instead of using a turbofan compressor in the engine like a normal jet does. This compressed air is then mixed with a fuel which, when burned, expands and creates its thrust. Although a ramjet can achieve speeds of up to Mach 6, they don't normally start working efficiently until its speed is over Mach 2, and as such they are normally launched by a small rocket to bring them up to speed before the ramjet takes over. In a nuclear-powered ramjet, the compressed air is channeled through the reactor core, which would heat up the air in the same way as if you burned the fuel. This expanded hot air is then what produces the thrust required. Even a small reactor core will create an immense amount of heat for weeks or months, effectively providing an almost unlimited fuel supply as far as the mission duration was concerned. Nuclear reactors of the time were usually large structures surrounded by lead and concrete, so to make one that would be small enough and light enough to fly would rely upon some radical advances in material technology, and this is where the ceramic core came in. The nuclear ramjet engine would also have to operate at temperatures higher than any conventional jet or rocket engine, whilst also being exposed to the intense radiation which would affect its electronic control systems, and it would also have to be able to fly for extended periods of time in any weather. With no pilots or active remote control like we see in military drones of today, it would also have to find its own way around. To do this, a new groundbreaking guidance system was developed called TERCOM. This used a downward-looking radar which compared its results to a terrain map which it carried on board. The flight path to the targets were then plotted onto the terrain map, and this would enable it to fly unaided deep into enemy territory. SLAM would also use an electronic inertial guidance system, control and telemetry, but these had to be made to withstand the intense radiation, as any standard electronic components would have been fried in a matter of minutes. With a fuel supply that could last for weeks or months, this gave it the possibility of being launched in a time of emergency, to fly around the oceans in a holding pattern close to the target until the order was given to carry out its mission. SLAM was designed to carry not one, but multiple nuclear warheads. The idea being that it would fly to its designated target, release its nuclear weapon before moving on to the next target, releasing its weapon, and then so on and so forth until all the targets had been hit, and doing so whilst travelling at Mach 3 just a few hundred metres above the ground. This is all pretty advanced stuff even today, but this was the mid-1950s. To test the prototypes, a section of desert locally known as Jackass Flats, which was around 310 square kilometres or 120 square miles, was set aside at the Nevada National Security Site, where the US tested its nuclear weapons, and ultimately where all the nuclear engines, including the Nerva nuclear rockets, would be developed. In order to test the system, they had to simulate the volume and temperature of the air that would be expected during its Mach 3 flight at sea level. This was well beyond anything any wind tunnel could provide, so they built a pressurised air supply using miles of 10-inch oil pipes bolted together to create a total capacity of 545,000 kilograms of air at a pressure of 3,600 psi. This was then passed through a massive heat exchanger to raise the temperature to 500 degrees Celsius at a flow rate of 325 kilograms of air per second to simulate the conditions that the ramjet's inlet diffuser would be expected to handle. So much air was required to do a 90-second test, but it would take 2 days to pressurise the system using huge compressors borrowed from the US Navy's submarine base in Connecticut. To create enough energy to propel SLAM and carry the payload, it was calculated to require a 500 megawatt reactor. But to test its viability, they first had to build a smaller prototype. This was called the Tory 2A and would be 1/10 of the power at 50 megawatts. Because the reactor core would be cooled by the incoming air, the pressures involved at Mach 3 inside the reactor core, not only from the compression of the air, but also the rapid heating, would be up to thousands of pounds per square inch in certain areas. To do this, the Tory 2A's air-cooled core would be made up of over 100,000 pencil-sized hexagonal ceramic fuel elements made from beryllium oxide and enriched uranium dioxide. These were stacked end to end in the thousands of airflow channels in the core, and because they were unattached to each other, this minimised the thermal stress on the system. The reactor was then attached to the ramjet, and the whole thing was mounted on a rail car that was shunted from its disassembly building to the test area by a remote-controlled locomotive. In 1961, the Tory 2A was test-fired for 45 seconds, and although the results were considered a success, it wasn't a complete flight-ready system. Its power was too low, and it had external water-cooled control rods in the reactor. The final test would need a full-size version that was completely air-cooled with the inlet and exhaust ducts fitted to prove they had a flight-ready nuclear ramjet engine. It would take 3 more years before the full-sized 500 megawatt version called the Tory 2C was ready for testing. This would be the size of a locomotive and weighed about 6,300 kilograms. Because everything in the reactor was air-cooled, the pneumatic actuators that operated the control rods which increased or decreased the power had to operate at 650 degrees C. If these failed or jammed, it would prove impossible to shut down the reactor once at full power. On the 20th of May 1964, the Tory 2C was rolled out to the test area and connected to an expanded air supply. The test ran for 5 minutes at full power, and after they had brought back the reactor and stripped it down for inspection, they found it had worked perfectly. There was no damage to the inside of the core or the pneumatic actuators or the electronics. The next stage would be to flight test it with a missile airframe, but the problem was where? They couldn't fly over populated areas of land as a crash could spread the highly radioactive material. So the plan was to launch it in the Pacific Ocean and then fly it around and then crash it into one of the nuclear test sites where the atomic bombs had been detonated. But SLAM would never reach its flight test stage, and on the 1st of July 1964 the program was cancelled. The world was changing fast. The shock of the Cuban Missile Crisis had led the US and the Soviets to banning above-ground nuclear tests, and as such, this would also affect SLAM. By 1964, ICBMs had advanced to such a point where they were seen as a superior system that was both easier to build and maintain, reducing the need for such a super cruise missile. There was also another reason. During the development, it was found that if they changed the design of the fuel rod slightly, the exhaust of the ramjet could be made highly radioactive. This would make it a vengeance weapon that would not only fly around dropping its nuclear bombs on its targets, but afterwards it could continue to fly at Mach 3, just 100 meters above the ground, not only causing damage with the huge shockwave it created, but also spewing out radiation and poisoning everything in its path until its reactor core failed, which could take weeks or months. The government decided that it was just too provocative and dangerous, and if they deployed this effectively unstoppable weapon, then the Soviets would be forced to develop their own version. Although SLAM was never made, much of its technology, especially the guidance system, is now used in modern cruise missiles. So, what do you think of America's Big Stick? Let me know in the comments below, and don't forget to check out some of our other videos. So, thanks for watching, and please subscribe, thumbs up, and share.